The small strain stiffness controls the soil response in a large number of situations. Imagine, for example, we have the case of a foundation, and when we apply the load on that foundation, the deformations are going to increase in depth. Primarily, they take place in the upper, this is the width of the footing, this is 1B, this is 2Bs, and the peak of the deformation tends to happen at B/2, let's say for a strip footing. Now, if I divide the settlement, divided the width of the footing, and let's say the classical 1 inch, 2.5 centimeters, and for a footing of 5 meters, so then this will be 10 meters in depth, and that 2.5 centimeters over the 10 meters depth is going to give us a strains in the order of 10 to the minus 3 on average. Higher at near the point where it eventually will yield, but quite small everywhere else. Therefore, the small strain stiffness plays a critical role in properly predicting the settlement of footings in general and all our geotechnical systems. Because we design them away from failure, away from yielding, so most of the material around will be in the small strain regime. Now, remember that in the small strain regime, particles keep their neighbors. We don't lose contacts. The coordination number between particles remains the same. Therefore, all deformation takes place at contacts. And please refer to a previous video on contact mechanics to remember the different type of contacts. In this case, let's say that we're going to emphasize the Hertzian contact. And so if we zoom in, we see particles subjected to normal load experiencing a contact flattening, and we anticipated that the tangent modulus of that deformation is going to be proportional to the applied stress normalized by the material of the mineral that makes the mineral to a power of 1/3. The other element that is important to recognize is that when we do wave propagation, including in earthquakes far away from the source, and if there is no site amplification, that propagation is taking place at relatively small strains. And all our laboratory studies are based on wave propagation at small strains, probably in the order of 10 to the minus 7, 10 to the minus 10. Therefore, wave propagation preserves the fabric, does not alter the fabric. The other alternative that we have is we can take a specimen and we measure deformations locally. For example, with a local displacement transducer or with locally installed deformation gauges. And so whether we do local displacement measurements and we plot the deviatoric stress versus strain, and we see that slope, or we are sending wave propagation through the system, we should get pretty much the same modulus. In fact, they are not necessarily the same. The static and the dynamic modulus have some differences, both in soils and rocks. But we are really talking about the small strain regime. And we are looking at that parameter. And so if we measure wave velocity from theory of elasticity, the wave velocity is a ratio between a stiffness and a mass density of the soil. Now, what is stiffness? If this is the shear wave, this is the shear modulus of the soil. And I want to emphasize the shear wave velocity because whether the soil is saturated or not, the shear wave really excites the shear stiffness of the skeleton. while if it is a P wave and the soil is saturated, it will also reflect the stiffness of the pore fluid that saturates the soil. So let's put emphasis on the shear wave velocity. And now this one tells us that the shear modulus of the soil is equal to the shear wave velocity squared times the mass density of the soil. Therefore, we are strongly encouraged to measure the shear wave velocity, particularly in situ, as well as in the lab. It's a very simple additional measurement that can be implemented in every device, odometers and triaxial cells and true triaxials, and with simple piezo crystals, Bender elements typically, we gain tremendous amount of information while at the same time we run the additional tests and measurements that we need to determine. So if I combine these two, now you realize that the stiffness in Hertz is related to the soil stiffness. And if this is the case, now I conclude that the shear wave velocity is going to be proportional to the applied stress normalized by some units, let's say kilopascals, to an exponent that now is the shear modulus, but the shear modulus is related to the state of stress, so it would be to an exponent beta and some alpha factor here. And that exponent beta from Hertz theory will be the square root of the cubic root, so beta will be 1 over 6 for Hertz. Now, if you have a rough contact, it's more sensitive, and the story gets more complex. So let's come back and investigate shear wave velocity propagation as a function of a state of stress for different materials, but the emphasis, once again, is to be able to go from the shear wave velocity to the soil shear stiffness. It follows from Hertzian type behavior and the fact that the velocity is a power function of the stress, that if we plot that trend, which is the shear wave velocity versus the confining stress or the applied stress, this is typically the trend that we observe. Notice that there is basically no stiffness if there is no stress, because it's like particles. In the extreme case, you could be running this in the space shuttle. Particles would not be exerting any confinement against each other. There would be no propagation. Now, because this is a power function, when I plot it in log-log scale, this becomes a line, and this is the shear wave velocity in logarithmic scale. So this would be 10, 100, 1,000. And this is the applied effective stress also in logarithmic scale. So this, where this is 0 in logarithmic scale, actually this is 1 kPa. And now I could have 10, 100, 1 megapascal, etc. So this power line becomes a straight line, and this is the exponent beta, and this is the intercept at 1 kPa, the value of alpha, where, once again, the shear wave velocity is equal to alpha, the state of stress, to the beta. Now, at this point, I have to add one more component. When the shear wave velocity propagates, let's say, in the x direction, but is shearing the material in the y direction. And so both the stress in the direction of propagation and the stress in the direction of polarization affect the shear wave velocity. There have been many attempts to figure this out. I'm going to put a reference there with Cascante, but so let's say that is polarized in one direction. This is the direction of travel, and this is the direction of polarization. then it will be the average of that one, of that velocity is the mean stress on the polarization plane, and we have to normalize in order to get the power, so this is kPa. So when both the mean stress, when both stresses are 1, the mean stress is 1, and we can say that at 1, kPa divided kPa is 1 to the beta, regardless of the beta. This is 1. Therefore, alpha is the shear wave velocity at 1 kPa, which is what we notice in this case. If I plot these trends for different soils, this could be for soft clay, this becomes for loose silt, this becomes a dense sand, and this is a cemented soil. As you can see, as the soils become stiffer, the alpha value increases, but the beta, the slope, becomes increasingly lower. So this is a summary of that data where I plot the beta exponent versus the alpha value. And remember, alpha is the velocity at 1 kPa, so this will be in units of meters per second, while beta has no units, it's the exponent. Materials with very low alpha value have a high slope, and materials with very high alpha values, like cemented soils, virtually have zero slope, and so the trend looks like that. If we were to plot here, where does a Hertzian contact fit? The Hertzian contact, remember, for velocity is 1/3 times 1/2, so this will be at 1/6, and so this is a Hertzian contact. Now, if particles become rougher, the contact becomes softer, and then it's more sensitive to state of stress. So this is the direction of angularity and roughness increasing. This is the direction of cementation. For example, a sandstone will have an alpha value, which is the velocity at 1 kPa, probably 3,000 meters per second, and the beta exponent may be 0.001. There's still a little bit of sensitivity to stress, but very difficult to discern. Now, what happens when particles become controlled by double layer theory? Well, if we put DLVO theory, or if we put just Coulombian interaction, QQ over R squared, the exponents here become very high, and so, for example, remolded Mexico City would be plotting somewhere here, Mexico City soil, with very high slope, in the order of 0.5, 0.6. So electrical interactions bring us to this point. However, cementation gives us a very low exponents. One more thing that I would like to highlight is that it's not just the contact type, it's also the degree of packing, because as we measure a soil, we are not only, as we increase the state of stress, for example, in an odometer, we are not only deforming the contacts. That would be great if it is small strain. However, in an odometer, we are also changing the fabric. And as you can see, this is a loose sand. This is the same sand, but under dense conditions. As the packing changes, we have more contact between particles, and so loose packings also have higher beta exponents. Please recognize the following. This is a subtle point, but it's very important. In order to make these measurements, I need to increase the state of stress. The measurement itself is small strain. Let's say wave propagation, 10 to the minus 9 strain level. However, the process of getting to different state of stresses may imply fabric changes. For example, when you squeeze a sediment in an odometer cell. So while the measurement itself is a small strain, what I'm checking here is the evolution of a small strain stiffness in a soil that may actually be experiencing larger strains and fabric changes. At the end of this presentation, you will see a slide that contains a very large data compilation from around the world and the expression for this alpha-beta relationship. Let's make a few more observations about the small strain stiffness and parameters that may affect it. So far, we've realized that the small strain stiffness will depend on the nature of the contact, the stiffness of the particles, the changes in fabric during your loading conditions, even though your measurement is a small strain. Now I would like to recognize a few other situations. One of them is, for example, when particles are subjected to a certain stress and they are submerged. What happens when drying begins taking place and there is a meniscus now that develops at the contacts? In fact, even before the meniscus develops, there is a surface tension that develops as the water begins to mobilize suction before air entry. This is far into the air entry situation. And so these additional forces are indeed going to increase the stiffness. So if I plot the shear wave velocity versus the degree of saturation under constant boundary stresses, you're going to see that the shear wave velocity at the beginning may start at high degree of saturation and 100 kilopascals, may start at 150 meters per second. However, it's going to begin increasing and increasing until a certain value, which reflects the evolution of suction in the soil. And that increase may be quite significant. In a sand, it may be only another 100 meters per second, but in a silt and in a clay, it could be very pronounced. It can bring us to 700 meters per second or more. Furthermore, at the end of saturation, that means when the soil finishes drying, then salts may precipitate and may give us a pike here. And so if we test the soil under unsaturated conditions in the field, we have to be very cognizant of the fact that if that soil ever gets saturated, it will lose stiffness because it will lose the contribution of capillary forces. The other one that is a very important effect is if we go back to cementation. We mentioned that one in the one on contact mechanics, and cementation could happen in different ways. Cementation could happen at crystals precipitate on the surface and have no effect, or it could be that crystals precipitate near the contacts, primarily during a drying process. This is the case of loess. Or it could be that crystals precipitate everywhere, probably because there was a biofilm. So this is during drying. This is just heterogeneous nucleation. And this is, for example, if there was a biofilm all around the particles, it will tend to coat the particles, let's say biomediated. Now, in all cases, we have to wonder what is the effect of these poor habits of cementation on stiffness. And now we can go back to what Hertz told us, that the tangent modulus, the small strain tangent modulus, is going to be proportional to the radius of the contact with respect to the radius of the particle, just to make dimensionality correct here, by the modulus of the mineral that makes the particles. And there is some factor here as a function of Poisson's ratio. And you can go back to the contact mechanics video. And so what is wonderful from this prediction of Hertz is that it is all about the radius of the contact. And as you can see, this one, heterogeneous nucleation, has no effect on the contact size. And however, in these two other cases, for the same amount of cement, mass of cement over mass of grains, Here the cement is distributed all around the particle. Here the cement concentrates on the contact. So this type of cementation that happens biased at contact, typically during drying, it could also form by pressure solution precipitation at greater depth, will have a very large impact on stiffness. So now, with this in mind, let's look at the evolution of shear wave velocity or stiffness with respect to the loading and cementation history. So we are going to plot the shear wave velocity in logarithmic scale and the stress in logarithmic scale. So these are straight lines. And now we begin loading an uncemented, freshly remolded sand or any soil. And we're going to follow the power equation, the Hertzian type behavior. And at that point, let's say at 100 kilopascals, we hold and we let the system evolve by diagenesis. Or we have put some cementing agent. Or we're running reactive fluids that will precipitate cement. And we're going to see a very significant increase in shear stiffness because of cementation. So this is the initial loading. And notice that once again, everything is sequence dependent in this case. So this is step 1. Step 2, we have cementation. And the stiffness increases quite dramatically. Let me give you an idea. If you take a drink with sugar, a Coca-Cola, and you run it through sand on top of a sieve, and then you let it dry, the water at the meniscus will precipitate the sugar, and that sand, before it began drying, probably had 40 meters per second velocity. After drying, it may be 700 or 800, and you touch it and you can't hardly feel it. However, the stiffness has increased dramatically, and that stiffness will be very important for settlement and for the evolution of destructuration of the sediment. So now what happens if during step 3 I decide to continue loading? Well, if I decide to continue loading, then the soil will experience almost no changes in shear wave velocity because it is cemented until it reaches the original trend where the particle deformation at contacts begins to catch up. Now, if the soil was loose, during this loading, the cementation may break and there is a structural collapse before it actually continues. This is a very critical situation where the cementation breaks. And this situation may lead, for example, for the collapse of layers in fly ash deposits or mine tailing deposits, and may lead to something like the Brumadinho failure. That very light cementation that we completely destroy when we sample the specimen may have a very important effect. So this is some structural collapse during loading, and will be primarily the situation where we have materials that have developed some diagenetic cementation. And then it goes back to the Hertzian behavior. Now, what happens if from this point we could have taken another path? Instead of continue loading, we could have said, okay, let's unload. Now, let's zoom in into the particles at this situation. So the particles were loaded, they experienced, and so they were like loaded springs. And now the cementation came, but the cementation has no load. The particle is carrying the load. So if you unload it, this spring wants to stretch out, and the cementation that had no stress all of a sudden is put under tension. So the cement will break here. And so during unloading, instead of unloading horizontally, actually it may experience decementation. And that is a situation where we sample these materials. Whenever we sample a material that has experienced some diagenetic cementation, even a rock, it does experience some degree of decementation. In soils, this can be quite critical. And then when we reload, we never get to see the original stiffness in situ, even if we put the specimen back into the state of stress in situ, that stiffness is lost. So at the end of this presentation, I will also include a slide where we plot, originally with Professor Ken Stokey, where we plot here the velocity in situ. On the vertical axis, the velocity measured in the lab at the same state of stress over the velocity in situ. And as you will see, there is a significant degradation of the velocity in the lab compared to in situ for most materials, except for soft materials that actually consolidate a lot when you reload them and may give you, in fact, an excess stiffness in the laboratory. Take a look at that chart. Summary: the small strain stiffness is all happening at the contacts, the formation at the contacts. In order to measure this evolution of a small strain stiffness with the stress, we are actually loading the soil, and so that loading process may not be constant fabric. And so what we measure with the stiffness, the small strain stiffness, is how that parameter, small strain stiffness, has evolved from one state of stress to the other state of stress. The measurement is at the small strain, the process is not. Of great importance to the small strain stiffness is not only the contact type, it's not only the state of stress, but is any degree of diagenesis, which may be significantly impacted during the sample process, not to be recovered during reloading in the laboratory.